Recently, video generation is rapidly evolving into a foundational technology for world models. These models are crucial for applications like embodied AI and autonomous driving, and at the very core of this evolution is the need for robust, camera-controllable video generation. However, to be truly useful, we must look beyond simplified scenarios. We need generalization to diverse real-world camera geometries, encompassing varying camera intrinsics and severe lens distortions. To understand the challenge, we first built baselines using current methods that rely on absolute camera encodings, such as direct parametrization or Plücker encoding. When testing these baselines on unseen real-world camera conditions, we noticed they immediately fail at basic motion control. And they completely fail at handling lens distortions, often breaking the image structure. We call this the absolute trap. While these methods attempt to encode full camera information, they suffer from poor generalization and limited controllability. So what is the root cause? It fundamentally comes down to coordinate sensitivity. The absolute values heavily depend on the setting of the world coordinate system. A simple shift in the coordinate system changes the input values entirely, even if the relative camera motion itself remains exactly the same. Same for the rotation in the coordinate system. The neural network gets confused by these drastically changing numbers. Previous solutions, such as P-rope, cleverly addressed this by moving from absolute positional encoding to relative positional encoding, calculating distances and transformations, specifically by interpreting the relationship as a transformation between local projective frustrums. This helped models generalize to longer sequences and unseen intrinsics. But P-rope has a fatal limitation, the pinhole assumption. Because it relies on linear projective transformations, it cannot model lens distortions. If you feed it fisheye or wide-angle footage, it simply fails. To solve this, we introduce UCPE, Unified Camera Positional Encoding. We decouple the problem into two complementary modules, Relative Ray Relationship that encodes lenses and poses, and Absolute Orientation that resolves the ambiguity of the camera's orientation in the very first frame. First is the Relative Ray Encoding. Instead of using absolute coordinates, we encode the relative transformations between local ray spaces. This handles both intra-camera lenses and inter-camera poses. Second is the Absolute Orientation Encoding, which is represented as latitude map and up map, providing gravity-aligned appearance cues such as sky-ground separation and object alignment. Let's dive into how Relative Ray Encoding achieves lens control. By mapping pixels to 3D rays, we capture the exact geometry of the lens. When conditioned on fisheye cameras, our method elegantly handles severe distortions. As demonstrated here with the unified camera model, UCPE natively supports a seamless spectrum of lenses, from standard pinhole to wide-angle and all the way to extreme 200-degree fisheye cameras. Similarly, for pose control, our encoding dynamically tracks the transformation between local ray frustrums across time steps. This allows for smooth, physically accurate camera trajectories, independent of any absolute world coordinate system, therefore generalizes to diverse camera trajectories by simply learning from how the rays move relative to each other. But relative motion isn't enough. The model needs to know which way is up. That brings us to our Absolute Orientation Encoding. We introduce a one-dimensional latitude map and a two-dimensional up map to explicitly encode the initial pitch and roll. This completely resolves the initial orientation ambiguity, giving the generated video a correct sense of gravity from the very first frame. To bring it all together, our Unified Camera Positional Encoding provides a comprehensive framework that achieves precise, decoupled control over three essential dimensions: the lens, the pose, and the orientation. To enable systematic training, we constructed a large-scale synthetic video dataset spanning diverse intrinsics, severe distortions, and complex camera motions. This dataset provides the rich geometric diversity needed for robust learning. With the data ready, how do we effectively integrate UCPE into existing diffusion networks? To explain this, let's briefly revisit the mathematical elegance of rotary positional embedding, or ROPE. In standard ROPE, the query token Qi and the key token Kj are each multiplied by their respective absolute rotation matrices, Ri and Rj. When computing the attention scores, we take the dot product of Qi and Kj. Following the fundamental rules of matrix arithmetic, we can expand and rearrange this expression with transposes. Because these rotation matrices are orthogonal, this operation beautifully simplifies. The attention mechanism effectively captures a single relative rotation matrix, Rij, applied directly to the keys and queries. This is how ROPE injects relative positional information. Our relative ray encoding operates on this exact same mathematical principle, but instead of using a simple 2D rotation matrix for sequence positions, we replace the matrix R with T, a 4x4 homogeneous transformation matrix representing our local ray space. The network intrinsically computes Tij, natively understanding the relative 3D camera transformations between any two tokens. In practice, UCPE is integrated via a spatial attention adapter. The block diagonal matrix of T is applied to the queries and keys. Remarkably, applying this to just one attention head is sufficient, adding only 0.5% of trainable parameters. We then linearly project the absolute positional encoding and add it as a bias before the attention operation. This entire module acts as a self-attention layer parallel to the original one, similar to LoRa. We use a zero-initialized linear layer at the end to ensure the pre-trained priors of the video diffusion model are perfectly preserved at initialization. Now that we understand the architecture, let's look at more results to see UCPE in action. Thanks to our unified design, UCPE supports a wide range of applications. As you can see here, it handles everything from dynamic cinematic content creation to robust world model for autonomous driving and embodied AI. For future work, UCPE's unified design and controllability clear the path towards precise camera control in real-time video generation or world models. Thank you for your time and attention.